So, welcome to our information event about our new study program on sustainable chemistry here at the Justus Liebig University in Giessen. My name is Hermann Wegner. I'm a professor of organic chemistry, and I will introduce you to our study program, where Giessen is, tell you something about the university, and also tell you something about the courses and classes which you can expect when you start studying the Masters of Sustainable Chemistry in Giessen. After that, 3 of my colleagues will present examples from their research in the area of sustainable chemistry. Maren Lepple is a junior professor in the Institute of Inorganic Chemistry, and after that, Jürgen, Janek, professor in physical chemistry, and in the end, Bernd Smarsly, also in the Institute of Physical Chemistry. Let me first start and tell you a little bit about Giessen, where Giessen is. So Giessen is in the heart of Germany, and Germany is in the heart of Europe. So if you look at the world, you can see there where Germany is. Probably some of you might know it currently anyways, because we have the European Championship in soccer right now in Germany. And then in Germany, Giessen is located in the state of Hesse. And again, Hesse is also very centrally located in Germany. And here you can see it. Giessen is right in the middle of the country of Hesse, of Germany. Additionally, it's just a little bit north of Frankfurt, which means you're very well connected to the Frankfurt airport, which brings you very fast to Giessen, and if you want to go somewhere, also very fast all over the world. On the right side, you see an overview of Giessen with the coat of arms of the city. Giessen is actually a quite old city. It was founded nearly 1,000 years ago at 1152 and is rather small compared to other cities with 80,000 inhabitants. As I said, it's 60 kilometers north of Frankfurt. Therefore, you have access to all the facilities of Frankfurt, which is with its museums, concerts, and all the other cultural offers. Nevertheless, Giessen itself has a lot to offer as well. It's the administrative center of the central Hesse, so therefore a lot of people actually commute into the city, so it doesn't feel as small as you might expect from the 80,000 inhabitants. Especially, there are a lot of two main educational institutions, and we have a large medical facility here in Giessen. And in these 2 universities, we have the Justus Liebig University, where the study program takes part, as well as the technical university, the Technische Hochschule Mittelhessen. And together they have 35,000 students. So with that, Giessen is the city in Germany with the highest student density. And that means we have a very lively atmosphere in the city. There are a lot of restaurants, pubs, and also activities. So therefore, there's really a wide variety of things for leisure, cultural, and also sporting opportunities. What the Giessen people are actually very proud of is their theater, because it has been built by basically the inhabitants of Giessen itself nearly 100 years ago, and there are really some nice performances done, and you see that on the top picture. But besides that, there are also several small stages and progressive theaters which also present plays on their own. We have a very independent music scene within Giessen, and there's a couple of bands which have made it to the national success. Also from sports reason, Giessen had a lot to offer. We have over than 90 sports clubs in all areas of sports. Especially basketball is very famous in Giessen, but also other sports like handball, football, athletics, canoeing and rowing, sailing, cycling, and dancing. Especially canoeing and sailing and rowing is a very good thing in Giessen, because we are very nicely located at the Lahn River. The Lahn River offers all kinds of recreational activities. You can go on the river, but you can also go besides the river while cycling or hiking. Unfortunately, Giessen was very much destroyed in the Second World War. Nevertheless, there is a very lively scene, and you see here a picture of the central street where you can do a lot of shopping and other things. But really, the main factor and the dominance in the city is the university, the Justus Liebig University. And here you see the main building of the university. It was founded over 400 years ago at 1607, and with that it's the second oldest university in the state of Hessen. It's the only German university which is named after a chemist, after Justus Liebig, which you can see here on the right side. He was the professor at the Justus Liebig University from 1824 on, and he was active in the area of organic chemistry, but also in a very applied sense. So therefore, he also worked into nutrition, applied his knowledge to agriculture, as well as he established a systematic training of students in chemical laboratories. If you come to Giessen, the laboratories, the original laboratories of Justus Liebig, are still present and you can visit them. And there you might have the feeling that Justus Liebig himself might just come around the corner and give you guidance when you do your experiments. But nowadays, we actually have much more modern buildings and facilities at the university, and we have different campi at Giessen, and the campus for natural science and life science is located at the Seltersberg, and here there are just three impressions from this campus. So it's very green. You have a lot of possibilities to sit outside. There are some cafeterias and some restaurants where you can get food and meet with friends. The chemistry department itself is actually very recently built. So we just moved in 2015, and therefore we have really state-of-the-art facilities doing chemical research and also chemical education. And as you can see, here is the picture. It's distributed in three parts. So the long building part, which you actually look at, that's part R, where mostly administration and the teaching labs are located. In the back, in this U-shaped structure, there are all the research laboratories located. Additionally, behind the building, we see the part C, and that's where the teaching mostly happens, because there are all the lecture halls, and that's actually where we are currently right now. So therefore, Giessen is really, if it comes to chemical education, one of the best equipped and most modern facilities you can find in Germany. So why study chemistry in Giessen, or why study sustainable chemistry? And I think there's actually, that's obvious to everyone. The world is changing, and one major driving force that is climate change. And we all know that the ice is melting at the poles. On the other side, we have increased heat all over the world, which leads to dryness and also to loss of crops and everything. At the same time, in other parts, we have a lot or too much water, and we have flooding, we have extreme flooding, which actually leads to injury and a lot of death. And if you don't cope with that, this will go on and will get worse and worse. And this has been recognized, and therefore it has to be changed. And one approach is to do that with sustainability. And sustainability goes further. Sustainability is not only climate change. Sustainability has three aspects. It's an economic, an ecological, as well as a social aspect in this thing. And the idea is that we have this goal to make the world livable for a long time for all kinds of people. In that way, we have all kinds of aspects which go way beyond just the climate change, and this has been summarized in the 17 sustainable development goals, which you can see on this slide. And now you might ask, what is chemistry contributing to this? Actually, it does a lot. And I just want to mention a few examples within these SDGs, the 70 SDG, where chemistry can or has contributed. For instance, if you go to SDG 2, which is zero hunger, and that's obviously a problem. How do you feed the ever-increasing world population? So you need special agents to actually increase the efficiency of crops. For instance, if you have this drought protection for crops. You have to have fertilizers. But one of the major elements involved in fertilizers is phosphorus. And phosphorus is getting more and more scarce, so therefore we need methods to recover it, and that's obviously a chemistry problem. And also you want to have targeted crop protection, and this is something where you really only protect your crop and don't harm the other environment. Another aspect is, for instance, that you have good health for all human beings. And here obviously you want to have also a good environment, and that means if you have chemical production, you should go to greener chemical manufacturing to actually improve the living conditions for everyone. Or if you go to drinking water for all, this is not possible in all areas. Therefore, it's a chemistry question. How do you provide clean water to everyone? And one option is, for instance, solar-assisted desalination process, or you have specific techniques to remove heavy metals or something to make water drinkable. Another aspect is that you want to have energy available for all people. And here, obviously, this is a pure chemistry problem. And chemistry can provide new ways of harvesting energy and actually storing energy, and we'll see later some examples on up-to-date research topics. Also, if you think about industry and manufacturing, here chemistry plays an important role because all the basic resources, all the starting materials come from the chemical industry, and if you have here sustainable processes, this will really impact the whole chain of industry. Also, if you think about resources, then you have to think about how can you use bio-based feedstocks, how can you use secondary generated biofuels, how can you actually use the materials which we already have used by doing recycling, and that's obviously is an inherent chemistry problem. And finally, climate change. This is obviously something where chemistry can also have an impact, and here we have to come up with design principles for green and sustainable chemistry to use that to address this aspect. So therefore, I think the study program which we now start here in Giessen at the winter term here will address this and will educate students to actually address these challenges and come up with solutions. And this is an international study program, so will be taught in English, and the idea, I think, is exactly what we have to do. We have to bring people together from all over the world to actually tackle these challenges, because one country cannot do it. And so therefore, I think this is an additional aspect why this international masters is really important and can make a difference, and everyone studying it can make a difference. Here you see the overview of our study program. It's a 2-year program, and they're basically divided in one lecture part, which is the first year, and then we have the second year where most of the research is happening. And in the first year, we have 6 mandatory modules, which I will go through in the following, and you have 4 elective modules where you can actually choose your own specialization. And I think that's something which is very important, because as we have seen, sustainability and also sustainable chemistry is a very wide field. And so therefore, it's very important that you can also look into other topics and maybe also go beyond just the chemistry part of sustainability. And then after you have got the basics and some tools to do sustainable chemistry, you can do your own research project in our research facilities. And there are 3 research modules in the first part of the second year, and then this accumulates in your master thesis. The first class you have to take is Introduction to Principles of Sustainability. And here we first just introduce you to the basic concept of sustainability, which definitely goes beyond just chemical aspects, but obviously we will use chemistry to illustrate some of these aspects. And this is, for instance, the complexity and also the interdependencies of these concepts of these factors. For instance, if you think about relationships between global warming and chemical processes. A second class, which is in the first term, is a seminar on new frontiers in chemical sustainability. So here it's up to you to actually get involved in one of the topics, which you can, in principle, also choose by yourself, to really dig into that, see what are the factors, and then present it to your fellow students and the tutor, and really get involved what is at the forefront of sustainable chemistry research. The third mandatory class in the first term is basically sustainability in organic reaction, and here we will introduce you to the concept of green chemistry. So green chemistry is not the same as sustainable chemistry, but green chemistry is a subset of sustainable chemistry. Because in green chemistry, it's really the clear metric, what is green chemistry, and here in this class we will see how what are these basics, what are the concepts of green chemistry, what are the parameters to apply them and to evaluate some of the systems. And therefore, this will be also introduced in this class. In the second term of the first year, we will move to inorganic chemistry, and here we will address especially aspects of recycling, recovery, and also of criticality, because obviously there are a lot of elements which have very specific properties, but they are not abundant in the world. And so one thing is, how can we reuse these elements, but maybe also how can we actually replace them with something. And these will be all aspects which we address in this class, where we think about, okay, how can you synthesize these inorganic materials in a sustainable way? How can you actually understand, by having structure property relations, how can you replace these compounds? And then in the end, obviously, how can you recycle them, recover them, maybe use like urban mining to regenerate these elements. Furthermore, we have a module about sustainable energy technology, which is very physical and physical chemistry based. So therefore, we will actually learn what are the basics of these sustainable energy technologies, like the thermodynamics, the physics, and the kinetics, which are behind this concept. And these will be then applied to problems like energy harvesting, for instance, by solar, mechanical, or thermal technologies, and especially how can you store the energy. Now, if you go to energy storage, how can you use that for transport and conversion? Another aspect which might not directly be obvious in the context of sustainable chemistry, but that's circular economy, because obviously we want to see how can we incorporate chemical processes in a circular way, that we actually can use everything which is produced, what might be side product, in a useful way, and especially make this then also economically viable. So there again, concepts like recycling of compounds, we do life cycle assessment, and we think about renewable resources. Additionally, you have the elective modules, and here they are very free. You can choose whatever you want, and here just a few are mentioned. So for instance, if you want to have like a specific topic in the sustainable chemistry area, for instance, sustainable water treatment, you can learn more about sustainable material chemistry. You can go into the basics even more and take, for instance, a class like physical organic chemistry. But you can also go a little bit away and say, okay, I want to learn something about innovation management for natural scientists. I want to go into risk or quality management, and here you can take basically everything you want. And then in the second year, you can actually apply everything you've learned in a research project. And here you have two research models within a lab work and a research group, and then a laboratory project also in the area of sustainable chemistry. And then in the end, you have the master thesis in a specific research group. And here you just see an example of my lab where we work on flow chemistry, for example. But there are lots of different possibilities in our department. For instance, you can work on new materials, and here a colleague like Professor Müller-Buschbaum or Maren Lepple, which will present some of their research in the following talk, or Bernd Smarsly, who you will meet at the end of the presentation. Other concepts like catalysis with Professor Schreiner, theory, Professor Mollenhauer, or green chemistry, Professor Göttlich, or Jürgen, Janek, and myself in the area of energy storage, just to name a few examples. And Professor Janek will also show a few examples of his own research later on. With the masters in sustainable chemistry, you are perfectly equipped to work in all kinds of areas. Obviously, you can continue your research in the chemistry area, for instance, by continuing with a PhD, but you can also go to other industries or other laboratories. You can go into development evaluation, you can do regulations, you can do to environmental organizations, authorities, politics, or work into education with a sustainable background. How do you actually get now to Giessen? How do you get into this study program? So what do you need? So first, you actually need a bachelor degrees in chemistry or related studies. Obviously, it's an international master, so we have to somehow use the same language, and that will be English, so you have to show that you actually are fluent and in written and spoken English. In Germany, there are no specific study fees. However, there's a semester contribution of around 300 euros, but this includes like a train, bus, and subway ticket for the whole state of Hesse. There's support of the Studentenwerk, which is dealing with accommodation as well as Mensa, so like student cafeterias. It also provides you with chip card. You can do bicycle renting and all kinds of other things. So in the end, I think Giessen is the perfect place to do these chemistry studies, and I think now is the time to actually do something to change our world and get involved in sustainable chemistry. If there are any additional questions, please contact me. The details are on the slide, and we will also introduce them, show them again at the end of this presentation. Thank you very much. With that, I will hand over to our next speaker, which is Professor Maren Lepple. And as I said, she is in the Institute of Inorganic Chemistry and will show you something from her recent results from her laboratory.
Thank you, Hermann, for the kind introduction. So my slides are there. Okay, perfect. So, as Hermann already said, I'm a professor for inorganic chemistry with the focus on materials and energy. And my background or my focus is on ceramic materials for energy applications. And so I want to present today some of our research dealing with new ceramic materials for more sustainable energy conversion. So first, I would like to introduce you to the class of ceramic materials. And as you can see on the slide, actually we encounter ceramic materials in our everyday life in totally different areas of our life. So ceramic materials have been used for a very long time already. So for example, for history in arts, but also like our dishes or our sanitaries. And of course, they have been introduced with industrialization also in industrial applications and are used in the process industry, medical engineering, mobility, communication, and energy applications. And ceramic materials are classified as inorganic, non-metallic materials, and usually in technical applications, oxides, carbides, nitrides, borides, and silicates are used. But as you will probably see in the talk of Professor Jürgen, Janek, also sulfides and halides are now coming more and more into play, especially in energy-related applications, and they can also be counted as ceramic materials. And ceramic materials are used, as I already mentioned, in a variety of energy conversion and storage applications, and I just picked a few. So they are used as active materials, for example, in batteries. They're used in gas turbines. They're used as catalysts or as support for catalysts. They're used as ionic conductors in fuel cells or electrolyzers, and they're also used in thermal absorbers. And with the technological advances, we now there's a higher need and demand for new materials, and they also have to have new functionalities. And by developing new materials, we also need to consider sustainable aspects. And now I want to introduce to our research on new materials for gas turbines. So you may wonder, like gas turbines or the combustion of fossil fuels is not the most sustainable way to convert energy. However, it's still one of the only techniques to propulse airplanes, and therefore also research in this area is needed. If we look closer at a turbine, we see here like a picture, and we see here, so here the air is sucked into the turbine, pressurized, and then here's the combustion chamber where the temperature increases. And in this area, in this hot area, we have these turbine plates, which are manufactured from metallic materials. However, they have a white or yellowish coating, which is the ceramic material. And you can see on the right side of your slide a section through such a turbine plate where you can see the substrate material made of nickel-based superalloys. Then on top we have a bond coat, which during operation forms an oxidic layer, aluminum oxide in this case, and on top we then have the ceramic thermal barrier coating material, which protects the metallic substrate from the high temperatures, but also from the harsh atmosphere. If we then look on the temperature distribution in such a turbine, we can see that this temperature increases up to 1600 degrees centigrade, and the higher the temperature of the combustion, the higher the efficiency. That means we need less fuel and thereby have less CO2 emissions. And on the right side in the slide, you can see that over the years, the temperature in the turbine increased. First, by developing these metallic substrate materials, starting from conventionally cast nickel-based superalloys, then directionally solidified, and then going up to single crystalline materials. And during the 1980s, the ceramic thermal barrier coating material was introduced, and by applying such a top coat on the nickel-based superalloy, the temperature made actually a jump, and thereby the efficiency made a jump. However, we want to go further, and therefore we need new high temperature materials. So the first approach I want to show here is actually to find new ceramic top coat materials that can withstand temperatures above 1200 degrees centigrade. So at the moment 1200 degrees centigrade on top of the surface of such a turbine plate is maximum temperature, and this is achieved. So there's a difference between like the combustion temperatures, which is around 1600, and the 1200 degrees centigrade, and this is actually achieved by active cooling. And by increasing the combustion temperature or the surface temperature in 40 degrees centigrade, we actually can increase the output power by 8 to 13%, and also can increase the cycle efficiency up to 4%. What we are doing, we are investigating new materials class, the so-called high entropy materials or high entropy oxides. And the idea behind this, it was already applied in 2005 for metallic alloys, and in 2015 it was transferred to oxidic materials or to ceramics in general, that we go from one corner of a multi-component system into the middle of a system, which is usually not investigated that well, and thereby gain new properties. And these properties are thought to be introduced by a high configurational entropy, which we achieve by mixing multi-elements in equimolar amounts. And this high configurational entropy would then lead to an improved high temperature stability just by the Gibbs equation. Also, we would have high lattice distortion effects, and lattice distortions increase the phonon scattering, and thereby we have low thermal conductivity. There's also a sluggish diffusion effect, which leads to a low sintering tendency, which is important at these high temperatures. And since we have a high variability in composition, we can actually design special properties to the needs, and also we can replace scarce elements. So regarding the properties, such as thermal barrier coating or such a material has to achieve, first is the long-term stability at high temperatures, of course, then a low thermal conductivity, because we want to have a way to protect the nickel-based substrate material from the high temperatures. We also want to have a low sintering tendency, because usually we have this columnar structure or porous structure to further reduce the thermal conductivity, and we want to maintain this structure. Also, we need an adjusted coefficient of thermal expansion for the base material, high corrosion resistance, mechanical properties, and also thermocyclic stability. And for the high entropy oxides, which we investigated, we actually can see here. So we obtain a material with a mixture, like a homogeneous distribution of the elements in the microstructure. On the right side, you can see a phase diagram where we have the temperature plotted against the radius ratio of the rare earth element, in this case divided by the radius of zirconium. And so you can see that actually, depending on the phase we have, so either defect fluoride or pyrochlore structure, we have transition temperatures above 1500 degrees centigrade. And that's the temperature where also the materials are synthesized. So they are stable up to very high temperatures. Then looking at the low thermal conductivity, we actually achieved thermal conductivities way below the currently state-of-the-art material, which is 7 YSE, so yttria stabilized zirconia. You can see like the benchmark value of approximately 2 plotted with a dashed line, and our values or the materials of the high entropy oxides are below 1, so which is a decrease, high decrease. When we look at the low sintering tendency, here we can see also compared the high entropy oxides compared to the yttria stabilized zirconia. And so we heat treated the high entropy oxides even at higher temperature than the yttria stabilized zirconia, and we see that the sintering tendency is much lower. So usually for thermal barrier coating materials, for example the zirconates which we investigate, we use a lot of rare earth elements which are quite scarce, and therefore we want to replace them. And we want to do it with the use of transition metal elements as shown here. And actually one of my PhD students is working on this, and she managed to introduce iron on the sublattice and got a phase pure material using two different synthesis techniques. So the further strategy is that we do not only use or try to use less scarce elements, but also try to find compositions which can be synthesized from ores, that we do not first have to separate each element from the ores and then mix them together again, but canceling actually the step of separating the elements and thereby reducing the energetic effort and also the costs. The second approach is that we combine the new TBC materials with actually new refractory alloys, and this is what we are doing in a joint project with the University of Bayreuth. So there we are now introducing, instead of the nickel-based superalloy, a chromium-based alloy as the substrate material. And the advantage is that chromium has a lower density than nickel, and thereby we can reduce the weight of the turbine by 11%, which also reduces the use of fossil fuels. And also chromium and silicon, which is also used in this alloy, are more abundant than nickel. So by implementing this new material composite, so chromium alloy and high entropy oxide as TBC material, we can actually reduce the active cooling component because all materials can withstand higher temperatures, and thereby we can avoid the loss of efficiency which we usually have by this active cooling of approximately 4%. To go to even higher temperatures and to also reduce the weight of the turbine, we can then use ceramic matrix composites, which is shown schematically here. So going from the first we introduced nickel-based superalloy with the TBC, then have a ceramic matrix composite actually as structural element. However, since it's usually made out of carbides, we then also use environmentally barrier coating, so protecting the structural material actually from oxidation. And there's quite a funny story behind this. So actually the Institute for Defense Analysis mentioned that pigs will fly before ceramic materials will fly. However, GE proved them wrong, and actually the CMCs are already flying. So not the turbine vanes, but other parts in the turbine are made of CMC material, so ceramic matrix composite. So what we gain with this ceramic matrix composite is the weight reduction, a higher fuel efficiency, longer service life, cleaner exhaust gases, more flexibility in the design, and also cost savings. And here you can see the two turbines and also the different airplanes where actually the CMCs are already used. Besides finding new materials to have more sustainable and more efficient gas turbines, there's also that alternative fuels can be used. So since there's no really alternative propulsion techniques besides solid oxide fuel cells, the industry is also looking for new fuels, and the one which is already used is the so-called SAF, so sustainable aviation fuel, which is composed of recycled cooking oils. And if we look over the entire life cycle, then we have 80% less greenhouse gases. At least that's what industry states. Then there's also the so-called wet engine by MTU Aero Engine, where they recirculate the excessive heat and thereby increase the efficiency. And they introduce the condensed water from the end of the turbine in the combustion chamber and thereby have a wet combustion. And by this wet combustion, the reduction of NOx gases can be reduced. So in total, with introducing the wet engines, the fuel consumption can be reduced, thereby the CO2 emission, the NOx emissions, and also the contrail formation. And what actually might replace the fossil fuels will be the hydrogen combustion. However, for both the wet engine and the hydrogen combustion, the materials have to be actually adopted. So for materials development for these new types of gas turbines, they have to withstand water corrosion, which is very corrosive at this high temperature. However, with these new techniques, so I have a slide here which shows actually the reducing climate impact by introducing the new techniques like the SAF or then the wet engine or the combustion or co-firing of hydrogen or totally use of hydrogen. So I hope by this short talk I could show you that ceramics are very important for technological advances, and new ceramics, for example the high entropy oxides for high temperature applications, allow the increase in efficiency of the gas turbines, the increase in power, decrease in active cooling and avoiding efficiency losses, decrease in weight, and also the materials have to be targeted, or the development has to be targeted for the new combustion atmospheres. And with this, I want to thank you for your attention.
Okay, thank you for watching and listening to our new master course in sustainable chemistry. My name is Jürgen Janek, and I'm a professor in physical chemistry focusing on electrochemistry. And it's my great pleasure to contribute to a number of modules and courses in this program. So the subject of my short presentation is sustainable chemistry for our future energy supply. And energy has always been one of the subjects in the natural sciences that interests me really quite a bit for several reasons. And of course, one of these reasons is simply the fact, and this is, I think, quite clear. Yep, it's progressing. What you see here is, I'd like to extend a bit more on what Hermann Wegner already has introduced, and that is our climate change. What you see here is one slide briefly entering into the question of energy storage, you may say, during the development of Earth and the, let's say, geological history. And what you see here in the upper little graph is the CO2 concentration in the atmosphere, which 60 million years ago was relatively high with 2000 ppm, and then declined simply due to, you could say, sequestration of carbon in the ground by the formation of carbon, oil and gas, mineral oil and natural gas. Well, if you translate that then into temperature of the surface of Earth, you see there's a direct correlation. So we see that the lowering the CO2 concentration in the air lowers the surface temperature on Earth. And what we do, please take care, this axis, the time axis, is quite stretched to the right, whereas we have the left half of the graph to 60 million years. On the right side, there's only a few hundreds of years. You see that what we currently do is simply digging out all this sequestrated carbon, burning it, creating CO2, and we increase within a very, very short period of time the carbon dioxide concentration in the atmosphere so fast that, of course, this strong non-equilibrium process, quite a number of things can happen that we probably cannot perfectly predict, but we see already the first consequences of that. And in the graph at the right side, you see that I think it's, yeah, now it's coming, okay. And you see here that in the worst case scenario, of course, we would, if we don't mitigate that problem, we will end up where we started 60 million years ago, with very high temperatures, quite above the level we currently experience. And well, of course, one of the reasons that this happens is that something happened in 1769, and that is simply that James Watt invented the steam engine, which was really a major advancement of human mankind, but which at the other hand, of course, gave us the tools to increase the carbon dioxide concentration to levels that will, in another sense, bring us back probably some 10 millions of years. So what we do essentially, we, in a certain sense, we take out carbon from this storage, which has developed over quite a long time, and change our climate over a very, very short time by manipulating that. So, maybe just a few numbers. What you see here is a table where the red marked line marks simply the natural gas. We see that in order to get 10 kilowatt hours of energy, so this unit 10 or kilowatt hour, the watt is joule per second, and then the hour, of course, 3,600 seconds can be easily calculated into joule. That with about 2 kilograms of natural gas, we can create about 10 kilowatt hours of electric energy by the appropriate, say, power plants. But the efficiency of these power plants is relatively poor, with only 40%. And one of the things which is part of the electrochemistry, the undergraduate curriculum, is that, of course, electrochemical devices can have much higher efficiencies, so that electrochemistry can be a good solution for that. So now, obviously, we can't really use this, let's say, nature's concept for storing energy, because you can't quickly return everything and come back to carbon. We would need to sequestrate huge amounts of carbon dioxide from the air, which is technically not manageable. So the only chance we have is, in fact, we need to reduce our consumption of fossil fuels, and then to harvest energy differently. And then, however, because this is, of course, happens not exactly, it's simultaneously with our demand, we need to bring up other concepts for energy storage. So what we have to do, and there is only really one reasonable solution for that, is we have to harvest renewable energy, as I said, either wind, solar, water, or thermal. And then either we use these energies directly as renewable energy. For example, that would mean you harvest with a photovoltaic device and directly charge up a battery and use it. Or, well, we store intermittently we store these energies as renewables in suitable devices. And one of the best ways to do that is, in fact, chemical or electrochemical storage. And I think what is a very important point at this, or conclusion at this early point, is for all energy technologies, and that's why I think energy technologies, of course, are an integral part of this program. We need materials, and for these we need chemistry. So materials and energy, that is really a nexus that is really very closely connected, and materials and chemistry are as close connected. So without proper chemistry, no new and advanced energy technologies. So here's just a little cartoon showing a bit how the relations are of the different storage technologies. You see, of course, mechanically, you can easily store energy by pumped hydro. You pump water simply up. And then, of course, you can also heat up the water, or you can simply take water and decompose it to hydrogen and oxygen. You see, of course, chemically, what we can, with this, the decomposition, the breaking bonds, we can store much more energy than just by heating water. So, as a student, you would know when you start increasing the molecules to vibrate, or just by taking everything up in the gravitational field of Earth. So that means chemical energy really is the right way. I think there would be even more, of course, if we could use nuclear fusion as a storage mechanism, but this is beyond, I think, what chemists would do. And then going to electrochemical energy storage, which is something I will introduce in a minute. It's really one of its biggest advantages is that it scales really over a wide range of orders of magnitude. So what you see here is in the bottom line a cardiac pacemaker, which only has a weight or a mass of about 2 grams. You store enough energy for, let's say, operating this pacemaker for more than 10 years, sometimes even 20 years. Then you know your smartphone and so on. And if you go then to the top line, for, let's say, 1 day of wind energy of a huge big 6 megawatt turbine, we would already need about 100 tons of battery. So I think that then comes into a region where probably battery storage is not the right thing. We would then really go to chemical storage in chemical compounds like hydrogen, methanol, ammonia, whatever. But over these 8 orders of magnitude, batteries, electrochemical storage is really the most suitable way of storing energy. And this is why, and this is something you will experience day by day if you look into the media in your own life, batteries, I think, enter into any part of our daily life. And what you see on the left side is that, in fact, all over the world, we have almost 30% increase of demand for batteries year by year. And we need terawatt hours capacity, and that means, of course, hundred thousands, millions of tons essentially of batteries and the corresponding chemistry that is behind that. Okay, that brings me then into some essentials and basics of batteries. And what you see here is already a cartoon of a lithium-ion battery, which is today's most important concept for electrochemical storage. And I think the point I like to make here is that battery research is really highly interdisciplinary. So at the left electrode, which is the negative electrode of called anode, is mostly graphite being used because it can nicely store lithium. At the other side, the positive side, which is often called cathode, there's mostly metal oxides, unfortunately containing elements like nickel and cobalt that are not really scarce, but that are often found in countries where we don't like, for geopolitical reasons, don't like to buy these materials. So we have a geopolitical issue with the supply chain, and this is one of the reasons why working for sustainable batteries with elements that are more abundant is one of the key issues, of course. Organics is involved at the electrolyte side, at the separator side, polymers, metals for the current collector. So the whole, I would say, rich field of chemistry and materials is really being found in today's batteries, and that in fact makes chemistry and material science really a key basis for this key technology for energy transition. And I think, of course, this is a bit biased from my side as a physical chemist. I would say that electrochemistry has the chance to become the semiconductor physics of chemistry. You know, we are also in physics. Semiconductor physics is a major part of modern physics. Now, a lithium-ion battery, in fact, and what you see here as a cartoon, operates in a relatively simple way. It's nothing else than solution chemistry in the solid state. So the left green area is the negative electrode, which represents the graphite. The right side in yellow is the cathode part, the metal oxide, and the lithium during discharging of the cell simply moves from the lithiated graphite to the right side and relithiates the oxide. And by doing so, we, of course, gain energy from our cell, and we can, fortunately, so say, go the other way around. We can charge our cell, and then we relithiate the graphite, delithiate metal oxide, and this works so well that we can cycle these lithium-ion batteries thousands of cycles without major loss of storage capacity. And I think you experience that in your life. Of course, you also experience that your batteries slowly age over time, and this is something which is one of the reasons why even improved batteries are, I would say, in demand everywhere. Now, what is beyond the lithium-ion battery? I think we experience that batteries are inevitable everywhere, huh? Not speaking of pacemakers. I'm sure you will not already have a pacemaker, but I think you definitely would miss your mobile phone. And it requires more and more energy. Maybe you or your family already drive an electric vehicle and like to drive it over a longer range. You like to buy cheaper batteries and so on. So there is quite a, I would say, a range of demand for improved batteries. But anyhow, lithium-ion batteries are currently a dominating technology, but still, over the whole world, there is lots of industry companies working on improving lithium-ion battery technology. And what is very important is that, in fact, I think that's something I would like to emphasize. If you compare the carbon footprint of 100 kilometers of mobility, when you have an EV that is run with a battery and you get your electric energy from photovoltaics, from a hectare of a field with photovoltaics, the efficiency of that and the amount of carbon dioxide being produced is a factor almost of 100 lower than planting corn and then making simply an e-fuel out of that. So I think this is, with respect to mobility, absolutely unreasonable to drive with e-fuels. So let me go into one example, because I think lithium-ion batteries operate. They need to be improved. We have to work on different, I would say, concepts. There's sodium coming up. But one of the dreams of electrochemists is to use a very, very simple battery concept, that is the metal oxygen battery. And as a sustainable chemist of the chemistry course, I selected really a very, I would say, chemical example to show you that this is not just kind of electrical engineering, that this really goes deep into chemistry and into electrochemistry. The idea is simply to electrochemically burn a metal, and in this case a lithium metal, electrochemically with oxygen. And there's different cell concepts that you have here as cartoons, and the most, let's say, mostly used, or let's say investigated one, is at the bottom left side. We have this aprotic cell concept. Aprotic means you have simply a non-aqueous liquid electrolyte that connects the lithium metal with a porous carbon electrode, and you will see that carbon, of course, plays a very important role in various carbons in sustainable chemistry. And the oxygen comes then from the gas phase, enters into the electrode, gets electrons, forms a product, and this product, in fact, depends very much on the counter cation. What you see here in the bottom is the redox, you may say the redox scheme of oxygen from the molecule dioxygen to O2 minus, and depending on the counter ion, and in the middle is sodium and lithium. In the bottom we have something like this, the chemistry occurring in a solid oxide fuel cell, and in the top in an aqueous environment which is being used in fuel cells. Here we have the two cases, lithium and oxygen, that really are interesting for metal era, alkaline metal oxygen batteries. And let's look a bit deeper into that. If you know a bit about inorganic chemistry, you'll see that in fact lithium peroxide is a stable compound, and lithium oxide is a stable compound. In the case of sodium oxide, the peroxide and the superoxide is a stable compound. Sodium oxide itself is also a stable compound. The question is, what forms electrochemically? And we will see what is very important, that in fact species are formed that still have at least a single bond. So the molecule should still be kept, because if the oxygen molecule is broken up completely, then in fact it is very difficult to recharge this cell, because reforming the molecule takes too much energy, too much overvoltage heat, and express that in electrochemistry. So what happens is that we have here a graph where we have the capacity, that means the charge we take out of an electrochemical cell, and the left axis we have the electric potential. And discharging such a cell, a lithium oxygen cell, is very simple, and you don't have a huge overvoltage, you don't lose much energy, so the loss of energy is relatively small. But charging the cell, so reforming the oxygen molecule, causes high overvoltage. So it's really difficult. It's easy, let's say, to add electrons to the oxygen molecule in this alkaline environment, but it's difficult to get these electrons back. And it's particularly difficult because quite a number of degrading reactions occur. And the overvoltage gets very high, and we have to reduce this loss of energy. The red-shaped area, in fact, you see this graph is a graph with a potential or voltage x-axis, y-axis, and a charge axis, and the product of that is energy. So the red area is lost energy that is simply transferred to heat. And I think if you have older devices with a battery, you may remember that these batteries really often get quite warm when you charge them or discharge them, which is an indicator that they're not so efficient. Modern batteries, I think your modern smartphone or laptop will not heat up at all, which means that the batteries really have been improved quite a lot. So reducing this overvoltage and easing, so say or let's say helping to get the electrons back from the peroxide species or from the reduced oxidation species is something where we cooperated with a group in organic chemistry with Peter Schreiner, who's a specialist for small molecules, for functional molecules, in this case for molecules that are kind of radical molecules, and varying these molecules. And I think this is something which I think is extremely interesting for people interested in students in organic chemistry. You can really tune the transfer of electrons to and from the oxygen molecule. I will not go into detail, but that is something where really organic chemistry and the redox chemistry that can be used in organic molecules very much nicely couples with the inorganic world in batteries. So what you see at the left side is now, and this brings me to the sustainability issue. As I said, with lithium oxygen, well, this still today does not work very well. The problem of the stability of the organic electrolytes versus against these aggressive oxygen species is not really solved, and still today we have no really well-running lithium oxygen cells. And then a few years later, one of our PhD students, more or less by serendipity, really found that if you do the same with sodium metal, sodium electrolyte, otherwise everything is the same, you see this blue curve, which is, or this blue area, which is the loss of energy, gets rather small. You have very low overvoltage in both directions. And this is due to the fact that only one electron is being transferred to the oxygen molecule, and you get a superoxide. And this one electron transfer process in both directions works very well. And then you can take a carbon electrode and you nicely form during discharge these nice little cubes. Looks a bit like rock salt cubes, but this is pure sodium superoxide, which has the structure of pyrites or iron sulfides. And yeah, this is something that could be the path to a reversible metal oxygen battery. We still work on that. There's worldwide activity still in academia to overcome these issues, but for sure we need to spend quite some time to at the end come to real solutions for that. Okay, so what is the what will future research in electrochemical storage bring us, and what is needed? One topic was already mentioned by Maren, and that is solid-state based devices. And this is something I'm quite happy that the federal government and the state of Hesse agreed to fund a new center for electrochemical materials research or science, the GCLMAR, close to our chemistry building, which is closely also connected to our chemistry department and the physics department, where we have additional 3,000 square meters of lab space for master students, for PhD students, and for projects in this field of, let's say, sustainable electrochemical technologies with I would say, top-notch labs, a dry room for advanced operation without water to really operate also the sensitive chemistry of batteries. Another subject I think that excites me very much, and that may also be part of future work of students in this master program, is work within the cluster of excellence post-lithium storage. So Giessen, JLU is part of this cluster, and in the current period we are associated. In the next period we will become a true part of this cluster, And this cluster is the world's biggest research cluster on electrochemistry for storage beyond lithium. You see here the elements that are being involved. That includes primarily sodium-ion batteries, potassium batteries, but also the question whether magnesium, calcium can be used and utilized like aluminum and chloride to construct batteries. And for all these systems, new anode materials, cathode materials, electrolytes, organic, inorganic, are being needed, processing concepts. And what is very important, one of the biggest research areas in that is machine learning and artificial intelligence approaches. So data operations and also theoretical modeling to accelerate the development of new materials. Now with that, I come to the end and would like to just make one final comment on the sustainability issue. True sustainability is not a simple exercise, and proper judgment of sustainability really requires interdisciplinary cradle-to-grave life cycle analysis. And just one very short example from a good friend from Australia, Adam Best, who borrowed me 2 slides, and the question is natural graphite sustainable? Well, I think graphite is a textbook example of pure carbon. Everybody has these nice graphene layers, I think, in front of his virtual inner eye. And the question is that a sustainable material. And what Adam did here, put together some data for the carbon footprint of graphite to be used in a battery, in a lithium-ion battery. And the yellow bar is the carbon footprint. It is roughly about, well, it differs a bit, something between 5 and 10 kilogram CO2 equivalents per kilogram of graphite for natural graphite, and the dark violet bars, are the carbon footprint of synthetic graphite, which is simply produced by essentially electrically by taking carbon sources. Whatever, you can then graphitize them at 3000 K and create this artificial graphite, and you see that costs much more energy. But at the end, the natural graphite looks better. Most of the energy is in fact needed not to mine it, but just to make it spherical for the battery and to coat it. That costs most of the energy, as you see in this left diagram. But in fact, all the natural graphite is rather dirty, has to be cleaned. Only 1 kilogram graphite comes out of 10 kilogram of mineral stuff. And so it may well be that at the end, despite this picture on the right side, at the end, overall, the synthetic graphite is better, but it's not really not simple. You need very advanced analysis to judge it. With that, I think I'm at the end. Thank you for listening, and of course, I would be happy to see you here in Giessen. Can you say?
Okay, thank you very much for watching. And in my final presentation, I would like to show an example of contents of chemistry in our course. What you have seen so far in the exciting presentations of Professor Lepple and Janek are examples how chemistry can contribute, especially in sustainable energy technologies. And here I would like to show you that good command in chemistry, good knowledge in chemistry is also important in other fields where sustainability is an issue. And I would like to choose the so-called concrete problem, or concrete and cement. Just to introduce myself very briefly, I'm professor of physical chemistry and materials chemistry here at the University of Giessen. My research is oriented to nanomaterials, carbon materials, and conversion and structural analysis. But also, I will be a teacher in this master program as Professor Lepple and also Professor Janek. And I would like to show you what you might expect in one of the courses we will be giving in this master program. And I would like to give you an overview and show you some teaching contents which you will expect and which are important in our course and which make the course specific. Okay, let's start. You may wonder, okay, what is the material you will be using in your first semester, and one good example is a book which I really love. It's Sustainable Materials by a group of, not only professors, but students from Cambridge University who wrote this fantastic book, Sustainable Materials Without the Hot Air. And that could be part of the first semester course, Introduction to Principles of Sustainability. Here's the content scheme of this book. And the book is devoted to materials, but at the same time, of course, materials chemistry. And it has a concept which I really like and which will be part of our program, as it focuses on materials which shape our everyday life and also guides us what is important in that field. And I would like to start with a scheme which Professor Janek has already shown, namely the contribution to CO2 emissions. And if you look at these graphs, I have to look by myself, on the left side you see the global greenhouse gas emissions, which are enormous, and a huge portion of that is due to deforestation, but an even larger part comes from industrial processes. And if we look into these, you see that buildings, industry, and transport are the main contributors to that. But now, if we now look into industry, we see that it is just a few materials which contribute most to CO2 emissions. And this is one of the concepts of the book I just presented. 55% of the industrial CO2 emissions are due to just 5 materials, namely steel, aluminum, paper, plastics, and concrete, which is amazing. Now you may wonder, what does this have to do with chemistry? Well, I would like to show you that good knowledge in chemistry is important to understand the problem and also maybe to solve the problem. Now these values, they refer to making the bare product, not the final material. And just an example, if you take into account that steel is then used to fabricate cars and so on, the numbers get even worse. It means that steel, aluminum, paper, and so on even contribute more to CO2 emissions than making the bare steel. So it's justified really to say that these 5 materials account for a large part of industrial CO2 emissions just to make goods. What Professor Janek and Professor Lepple showed you is more relevant for the field of transportation, of course. Here we are now in making goods of our daily life. To sum up, so these are the 5 materials which really contribute a lot, and we will pick out now cement as an example. And you may wonder, why do you need chemical knowledge to understand the problem and also to find solutions? Why do we need knowledge in chemistry? Isn't it an engineering problem? Yes and no. Well, this scheme is similar to what we already saw. It shows that concrete, steel, and so on have a major impact on CO2 emissions. Yes, but what I would like to focus on now, and what you saw in the previous publications, you need to also be able to judge data from literature. So which sources and data are reliable? That will be an important part of our program too. Because numbers, reliable numbers, are very important in the overall discussion. Another example to look at is the way of presenting data. You can show numbers as they are, like the scheme before. But this kind of scheme you see here is one which has proved to be very successful and illustrative in the entire field. It's the so-called Sankey diagram. What does it show? Well, you have to look from left to right, and the materials we have been discussing are in the middle right, and what you see is what enters at the left. So it's natural resources and so on, and in the end you see the outcome, goods of our daily life, and you can also see how they are transformed. But not only that, you can only follow the flux and the width of the fluxes. They correspond to their contribution on a quantitative scale. So you will be also learning how to illustrate such data and to interpret them properly. Okay, now another issue which in the previous talks came already relevant, but which is important, to be able to handle numbers. And this is a very important topic in the field, and knowing how to calculate numbers, quantities is a very important part of our program in some of the courses. What do I mean with that? I would like to give you an example. Let's switch to steel, but we'll come back to the concrete in a second. Well, if you take the numbers we have just presented, steel creates a huge contribution to global CO2 emissions. Okay, but what is the contribution? Which number should we take? And you could take different ones and set them in relation to the overall CO2 emissions. You could take the CO2 emissions for making liquid steel, or the emissions for making steel stock product, or the emissions associated with the final goods, like a car, construction materials, and you see that the numbers are different. So which one is the right one? None of them. They correspond to a different question. Now, if you relate these numbers to other numbers, it's a question, which one do you take? And depending which reference you use, so overall emissions or just industrial sector, you see that the contribution of steel to the overall CO2 emissions can vary from 4.5% to 35%. You may ask, what is now the correct one? Well, none of them, but it's a question of interpretation. But you see that you have to be very careful, you have to rely on numbers, and you have to be able to judge the numbers, and this is also part of our program. But now I would like to come to the original topic of my presentation, which is cement. Cement was, people say, invented by the Romans, by the Roman Empire, for constructing buildings. And it is so successful because you can pour it like a liquid, which solidifies, and then you are able to construct fantastic buildings like the Pantheon in Rome, or let's say more technical buildings like bridges and so on. Well, just a maybe reminder what concrete and cement is. Cement is the binder material, which is mixed with sand, stones, and water. Very simple process. Cement contains aluminosilicates, or calcium aluminosilicates, different versions and different components. Finally, we use the cement to construct the materials. You can pour it, you can shape it, and that's the fantastic property of the material. What is the problem then? Well, cement is produced on the megaton scale per year, with increasing tendency, and especially in countries like China and India advance and require more and more cement and concrete each year. And this is part of the problem. And now we come to the chemical point of view. So what is the problem with cement and CO2? Well, there are two issues. You see from the bare reaction equation that the basic material taken from nature is limestone, calcium carbonate. It is heated to release calcium carbon dioxide, and leaving behind calcium oxide, called lime, which is the binder in the cement. The chemical processes are difficult, and that's not the main focus here, but it's a solidification in the presence of water which takes place. So you see that one has to understand the chemistry of cement production and the process of solidification to understand this process and maybe to change it. Now, what is the problem? The CO2 emissions by cement are enormous. In this graph, you see that cement looks quite small in contribution, but overall it is a huge contribution. So there's a need for either recycling strategies or to change the process at all. Another version, here you see the emissions according to different regions, and you see that China has an enormously growing demand of cement. And you cannot just say, okay, we stopped constructing buildings. No? Okay, you might stop, but who will take that decision? So this is not a real option. So we have to find strategies. Okay, so what do we have to know about cement production and so on? You see one example, the production itself. It's produced from limestone, it's heated up to produce Ca2. And so to understand why we need so high temperature to release CO2 and to produce calcium oxide is this phase diagram. So in our course, you will also learn how to interpret these so-called phase diagrams, so to learn which which structure, which material is stable at what temperature and which pressure. This is one important knowledge you have to adopt and to understand why CO2 is released. We have to have a temperature, high temperature, at which CaO and CO2 are stable, and where calcium carbonate transforms. Okay, let's go back. Let's go to this process in detail. Why is so much CO2 released? It's two processes which have to do with physical chemistry and inorganic chemistry. The first point refers to the phase diagram. High temperature and heat is needed to convert limestone into calcium oxide and CO2. It is a so-called endothermic reaction. We need a lot of heat to put that reaction on the right side. The second process is producing CO2 directly. The process itself generates CO2. So we have two sources of CO2. The one so far is fossil fuels are used to provide the heat. This releases so far CO2, and the other one is the inherent release of CO2 by the process. And overall, we produce 1 ton of CO2 per ton calcium oxide. Okay, so what do we have to know about that? As a student, what you have to learn is have to know thermochemistry, stoichiometry, because this reaction is an example of where stoichiometry is relevant. So for one, so to say, unit of limestone, 1 unit of CO2 is produced. And you cannot change that. It's always 1 to 1. Okay, so a lot of issues of general chemistry are involved, and as we have seen in the previous talk, it would be nice to provide the heat which is required not by fossil fuels, so burning coal and natural gases, but using electricity coming from renewable sources to provide the heat. And this is indeed a valid concept which people perceive. Now let's look at these numbers, and that's again the point. We need an energy of 445 kilowatt hours per kilogram cement. And how much is that? And this is again a part of our teaching to get a good feel and competence dealing with these numbers. So as Professor Janek already showed you, there are some examples to get a feel for these numbers. 1 kilowatt hour is 1000 watt hours. It means you can run a laptop 60 watt for 16 hours or something like that. So you could calculate how much that is in relation to making 1 kilogram of cement. It's running a microwave 1000 watt for 445 hours, and this is enormous. Okay, what are possible solutions? One solution could be recycling. I will give you an example, but so far this is really difficult, but with chemical knowledge there might be options. The simplest option would be to replace calcium oxide by other binder materials, and this is one strategy which people pursue, like demonstrated in this Nature publication. So one might use residues from from metal factories, from agriculture, ashes, and so on, to substitute calcium oxide. But this concept will work only to some extent, because the properties, of course, must be kept constant. But this is one option, and the question is, why would that work? Well, that's part of our course, which we discuss in detail. Now let's come to a more chemical approach, which also is proposed by a recent Nature publication. It's the electric recycling of Portland cement at huge scale in relation to steel production. What does that mean? Well, the idea is to use old, so to say, used concrete from old buildings which are torn down, to put as slag into the production of steel. So used steel coming from old cars and so on is put into these electric arc furnaces. New steel is made. This process needs sort of slag to protect the electrodes made out of graphite, to protect the steel against air, and also to provide good plasticity of this process. So the idea of this group is to use used concrete to put into this arc furnace as substituting the previously used dolomite flux. which comes from natural resources. And this actually has turned out to work quite nicely, as you see here. So on the left side, this reddish material is the slag, which is obtained after this process. And this material can be cooled down and used as substitute for Portland cement, to make bars of concrete, as you see an example. And the authors show that the mechanical properties are really exciting and similar to the standard Portland cement, which you can buy in the supermarket, so to say. Well, this was shown also by chemical analysis, as demonstrated here with XRD. So the properties were compared on the level of atomic scale of composition and so on. So what people have to know, of course, is knowledge in analyzing such materials, chemical analysis, X-ray diffraction, and so on. So you need to know chemical analysis methods to advance in that field. And by that, what one could show that the material which is created by this electric arc furnace process is similar to the perfect Portland cement previously used to make concrete. So this is really exciting. By that, I'm at the end of my little session, so to say. Well, some conclusion. We have to think big scale, and this is part of our teaching concept. Look at the large scale contributors to CO2 emissions and the chemical processes which are involved. This is the transport area, this is construction and agriculture and so on. New concepts need people, young researchers, having a good command in chemistry, because as you have seen, chemical understanding helps a lot to advance not only in transport related challenges, but also construction materials. So please feel invited to join this study program. I think it's exciting, and you will have fantastic knowledge and also for your future career. Thank you very much.
Yeah, with that, we are at the end of this info event for our new international master's program on sustainable chemistry. And I think you got a good impression what we are doing here at the Justus Liebig University in the Department of Chemistry to actually do sustainable research and to provide chemical solutions for day-to-day problems. And if you join the program here, you can be part of that. And so I think there are really great opportunities. I showed you the courses, I showed you the curriculum. If there are any further questions, please don't hesitate to contact me. I'm basically the leader of the execution board of the new study program. You find my details on the slide. Write me an email and I try to get back to you as soon as possible. Hope to see you all in Giessen. Hope to see you all in our chemistry department. See you.